So, type of organic reactions and reaction mechanisms. Reaction is something that we have been doing all along, but reaction mechanism is going to be something that is going to be a part of A levels because that is really a step up, that is something advanced. When we use the word reaction mechanism, it actually means to summarize the series of steps that happen during a reaction. So far, what we are doing is that we are representing a reaction with a simple chemical equation, and we usually assume that it's going to only happen in one single step. But that's not how that happens. Yeah, we do understand the simple breakup of a reaction that the previous bonds break and the new bonds form. So every student understands those two steps. The previous bonds will break in the first step, the new bonds will form in the second step, and that's how every reaction would go. But we usually assume that's going to happen in the same reaction. There won't be any more steps to it. But now what we are going to do is that we're going to explain it a little bit more so that you understand that it might be more than just one or two steps in a reaction. So before we get started, there is something we need to explain. There is how our covalent bonds can break. There are really two main ways by which covalent bonds break. We call them homolytic or heterolytic fission. Before I go with explaining these words, let me tell you the word homo means same. And we have been using this Greek term in many names in science, and the word hetero means different. Wherever you are going to see the word lytic, or lytic actually comes from lysis, okay, this means to break down. Okay? So homolytic fission or heterolytic fission means breakdown. Fission itself means breakdown of a bigger portion to give you smaller portions. That's what the word fission means. Although it might have different meanings in nuclear chemistry or nuclear physics, you might have been using this word in nuclear physics, fission and fusion, but fission definitely also means breakdown. So homolytic fission or heterolytic fission means same kind of or different kind of breakdown. Okay. So when this happens, it's really easy to understand what's going to happen in homolytic or heterolytic fission. First of all, the homolytic fission. Homolytic fission is pretty simple. When the covalent bond is going to break, what's going to happen is that atoms get to keep their own electrons. For example, hydrogen's electron is represented with a cross, fluorine with a dot. When this fission is going to happen, when I write it like this, we usually show it with a dashed line, that this bond is going to break. When that happens, you are going to see in some book, we show it like this. For arrow, there are two lines. What we usually do is that we don't draw the second line. It's a single-headed arrow. Single-headed arrows are usually shown on top of covalent bond signs, single lines I mean, to explain that the two electrons which were previously shared are now back to their original owners, back to their original atoms. So H gets to keep its own electron and Cl gets to keep its own electron. And that's what happened over here. The simple name, homolytic fission, same kind of breakdown. So the two electrons would, bond were broken down. One electron went to one atom, the other one to the other atom. So it's more like breaking in which everyone gets to keep the same percentage or same part of that bond. All right. Equal can also be the word, or mutual can also be the word which can be explained. Now, when this happens, what we get is that it might be pretty simple that they get to keep their own electrons, but what happens is that we're going to produce a new species, a species that we might have discussed in previous chapters, but even if we haven't, we're going to discuss it now. Now, take a look that there is only one single electron in hydrogen. If I look at chlorine, there is one pair, two pair, three pair, but then is again an unpaired or single electron. We usually call it unpaired electron. In organic chemistry, and unpaired electrons have very important roles to play. Now, when homolytic fission happens or bond breaks homolytically, they produce free radicals. What are free radicals? Free radicals are the species that have an unpaired electron, which is represented by a dot up top, and they are very reactive. So homolytic fission itself is not something that we consider important, but the product it is going to produce is considered very important. It gives us H free radical and Cl free radical. That's how we pronounce it. We don't call it H dot or Cl dot. That's not the way how we call it. We call it H free radical and Cl free radical. Free radical automatically gives the listener an idea that there is one unpaired electron on top of it. And when I say the word unpaired electron, it doesn't mean there won't be any more electrons in the valence shell. There can be, but they are supposed to be paired. Now take a look at it. One pair, two pair, three pair. There is only one unpaired electron over here. So moving on, um, we are going to study more about unpaired electrons or free radicals in section 15.2, but what we are going to discuss it over here is an important reaction that is taken up by free radicals, which is very important to explain as this is going to confirm about one specific kind of reaction mechanism. Now, the type of reaction which involves the formation of free radical is usually considered an initiation step. This requires input of energy to break the covalent bond, resulting in two free radicals, which is pretty simple. For example, you have this chlorine molecule. When you're going to break it down, single-headed arrows, this one and this one are going to keep their own electrons. So it's going to result in two chlorine free radicals. This specific step will then be known as initiation step. This initiation step is actually going to require energy. This happens usually with the help of UV light, ultraviolet light. And ultraviolet light is that input of energy which broke this covalent bond into free radicals, right? The free radicals formed can then attack reactant molecules. They generate more free radicals, and these reactions are known as propagation steps, and they kind of work like a chain reaction because they only stop when free radicals react with one another. Up till the point the free radicals keep reacting with other molecules, this process is going to keep going on. Now, you might have heard or you might have seen examples of free radicals back in photochemical reactions and back in the topic of destruction of ozone. Now, ozone is a layer which is blanketing the entire planet, and we are continuously saying from past 30 or 40 years that ozone is getting destructed because of a lot of pollution. And that pollution, we keep talking about the free radicals. Now I'm going to show you a reaction which is going to explain this propagation step to you. Ozone is actually O3. O3 can be attacked by a chlorine free radical. What happens is that it breaks one of the bonds of oxygen in ozone and it produces this. This is a bigger problem for us. It produces the chlorine oxygen free radical and oxygen gas. Now, the blanket at which ozone is present, ozone is much higher in concentration than the oxygen gas itself. That's why ozone is such a good, uh, we can call it a shield that protects us from the harmful UV rays. So those UV rays have the capability to actually break down any chlorine molecules present over there into chlorine-free radicals. And those radicals attack like this. Now, the point we were trying to make is that they attack reactant molecules, and in doing so, they generate more free radicals. Take a look at this. A free radical attacked a molecule, produced a free radical and a molecule. That free radical might be capable of reacting with more ozone molecules, which it actually is. And I'm going to show you a reaction in which it is going to attack on another. And again, see, a propagation. A free radical attacked a molecule, produced a free radical and molecule. This free radical can again attack another ozone molecule. That's why we call it a propagation step. Propagation means to keep going on. See, this loop would keep moving on and on. Because every time the entire set of this two reaction loop is going to end it's going to give us the same free radical, which is capable of attacking another molecule in the similar way. The only way the entire thing is going to stop is when the two free radicals react together. And I'm going to react, and this is written in these lines, and we call it actually a termination step. And I'm going to show you the termination step right over here. Take a look. A
Sir, I have
free
a question.
radical, go ahead.
Sir, the CLO is minus, right? -1.
No, it's not negative one. Okay, uh, very good question. Let me clarify. Cl dot means that Cl has an unpaired electron, which actually Cl atom does in the first place. Cl negative means Cl has an extra electron. Now, if I be explaining it more clearly, this is 287 and this is 288. So there's a difference between the both, and that's a great difference. This actually is the original atom. Makes sense? Now,
Yes,
I
sir,
am,
but what about in the CLO?
what about in what?
The CLO, because chlorine is bonded to oxygen, right?
Right. Chlorine is bonded to oxygen, but they have an unpaired electron as well. That's why the sign. That's the
Okay, got
best
it.
part. Whenever we are going to write a dot on something like this, keep that in mind. They have an unpaired electron as well as they have a bond, right? Now, I'm going to clear it up to you. Just a second. 287. And what's the configuration for oxygen? 2,
2, 6.
6, right? Now, one electron from here and one electron from here are going to make a bond. Let's suppose if one electron is going to make a bond, we are left with 2, 8, 6, right? And we're going to left with 2, 5. Out of these 5, imagine one pair, another pair, 4 electrons. Is there an unpaired electron on top of it, even after making a single bond? Is it? Yes, there is. And
Yes,
that's
sir.
that electron. Make sense? Or do I need to draw it properly?
Sir, I got it.
Good, great. Now, uh, the point I was trying, I forgot the point I was trying. Yeah, I was talking about termination step. So in the termination step, really, two radicals are going to react to form a molecule. This actually happens with chlorine gas. Chlorine do not exist in the form of atoms. Chlorine actually tends to exist in the form of diatomic molecules, which we call chlorine gas, which is this one. And we keep saying the chlorine is reactive, the chlorine is reactive. The chlorine is reactive. In fact, all of the halogens are reactive and they exist in the form of diatomic molecules because they actually are free radicals. And these free radicals are actually very reactive. And as soon as they get a molecule to attack, they do. If they don't, if they find another free radical, they form a bond. That's why all the halogens exist as diatomic molecules. Make sense?
Yes, sir.
This is now a termination step. So these are the kind of steps, and we're gonna pick them up again in the very next chapter, and we're gonna discuss about free radical reactions. And many photochemical reactions are going to be free radical reactions. Remember, when I use the word photochemical, I mean reaction with occur with the help of light. And back in IGCSE, there were three photochemical reactions that you studied. One was photosynthesis, right? This was first example of photochemical reaction that you studied in IGCSE. The second one was silver uh, halides, AgX. Their breakdown, actually they break down in the presence of sunlight. Silver and chlorine would actually break down into giving you silver and chlorine gas, or silver bromide, or silver iodide. Any silver halide will break down in the presence of sunlight. And the last was the reaction of alkanes with halogens, such as methane with fluorine. These were the three examples of photochemical reactions that you studied back in IGCSE, and we're going to pick this one up as this one belongs to organic chemistry and is easier to study. And we're going to study this one with the help of free radical reaction. This is what has been pointed out over here. Now, if I summarize all of this, which he has over here, there are three steps, an initiation step, in which free radicals start off a reaction. Initiation step may also discuss about the production of free radicals themselves, right? Like this was initiation step for us. These two were propagation step for us. This was the termination step for us. So for propagation, steps in the mechanism that regenerate more free radicals, like this one is doing. It is regenerating more and more free radicals. Now, the termination step, the final step in the mechanism where two free radicals meet and form a product molecule, is termination. And the same thing happened. Two radicals met and they formed a molecule. As soon as they form a molecule, uh, thanks to the termination reaction, we got rid of the more reactive species. Molecules are not as reactive as free radicals are, hence the whole propagation stops. Hence the name termination step. I hope this all makes sense to you. Does it?
Yes, sir.
Okay, good. Let's move on. Heterolytic fission. Heterolytic fission is something that you are already familiar with. This is uneven breaking of the covalent bond. And when this happens, we know that the more electronegative atom actually takes both electrons. What happens then is that it produces ions. Now, ionic breakup is something that we completely understand, but from covalent bonds, this happened less for us in IGCSE since there were very less examples of covalent bonds which broke up into ions back in IGCSE. We only used to do it with some unstable material. For example, in IGCSE, we have done it with ammonium hydroxide to produce ammonium and hydroxide ions. Maybe we have done it with HCl is one of the examples, and I really forgot the example. Yeah, um, carbonic acid. Okay, so these are the examples that we have considered really in which this is a very good example of covalent bond breaking. Okay, so that's why we're going to consider the HCl's example. Now we do understand that the chlorine's electronegativity is much more than hydrogen. Of course, chlorine gets to keep both electrons, and this one is Cl negative. This is heterolytic fission. This one is positive. The one that loses the electron becomes a positive ion. The one that gains the electron becomes a negative ion. In this case, we do not break an arrow into two halves. We properly use an arrow. The tail is always shown at the covalent bond. The head shows the atom which is more electron in the both of them, which means the one that is about to become a negative ion. So you would see these kinds of arrows. Now, these arrows are considered extremely important in organic chemistry. And when you're going to solve these questions or when you're going to look up their answers in marking schemes, you would see that there are separate marks for arrows. Sometimes they don't award you marks for arrows, but they do cut one if the arrow is incorrect. The kind of difficulty level we usually commonly face in Cambridge. So you're supposed to get your arrows right. Now remember, if a bond is broken like this and this, half arrows on both sides, it means homolytic fission. Now, since they both get to keep one electron each, or the balance of the whole breakdown, so half arrows. But if we do this, a complete arrow, that means the arrow is actually pointing toward the more electronegative atom, which is about to become an anion. Now, if this was normal chemistry, it might have been cations and anions. Since we're talking about organic chemistry, so really we're going to change the whole terminology. Let's discuss that. Okay, in case if the bond breaks and the Br atom in this example, as you can see, takes both shared electrons, it forms a bromide anion. This leaves methyl group with a positive ion, one electron short, of course, and we're going to call it carbocation, which gives us a very good idea that if any carbon-based ion has a positive charge like this one does, we are going to call it a carbocation. And if at any point, let's say this one has a negative charge, we are going to call it a carbanion. All right. Carbanions are not a big part of A levels chemistry, but their names are discussed here and there, very seldom. But yes, you must know it. That's why a carbocation or a carbanion. Any organic ion which has a positive charge, organic means it must have carbon in it. So any one with a positive carbocation, negative carbanion. Now, since we are at discussing the carbocations, let's discuss the types of carbocations. Now, carbocations are of three types. The carbon that has the positive charge, if that is backed up with one chain, R means alkyl group, carbon chain, it is known as primary carbocation. If it is backed up by two carbon chains, the carbon that is positive, it is backed up with two carbon chains, we call it a secondary carbocation. And if it is backed up with three carbon chains, we call it a tertiary carbocation. It's pretty easy. If it's not a carbon chain, it's probably is hydrogen or some other atom or group of atoms, but definitely not a carbon chain. If that happens, we call it primary carbocation, or the number of chains increase or changes the name. Now, we need to understand that this one is least stable and this one is most stable. When it comes to stability, there is actually the depth of organic chemistry which we need to discuss. How am I able to say that this one is least stable and this one is most stable? Plus, you might have a question why these kind of arrows and why this arrow? This definitely represents the simple covalent bond. What is this arrow then representing? So let's discuss, dive in deeper. We have something more important to discuss. Note that the carbon atom with the positive charge only has three covalent bonds, not the usual four, making it electron deficient. We understand why the positive charge, and hence it is known as a carbocation. Now, any alkyl group, CH3 or C2H5, C3H7, anything like that, or some other chain, it can be anything attached to the positively charged carbon atom tend to be electron donating. Now, whenever we are going to put up a chain over here, we are going to actually bifurcate them into two kinds of effects. Okay, effects have more name, but I'm going to discuss the generals, the basics, and then we are going to bifurcate it with proper names. So first of all, the electron donating effect. It's usually not named as this effect, but I am trying to explain the background of it, the basic chemistry. Then I'm going to go with the proper names of effects, and then affecting or withdrawing. Um, Actually, withdrawing is a much better term. Yeah. Let's not discuss this word. This is obsolete, not used anymore. So electron donating effect or electron withdrawing effect. Now this carbon is feeling positive since it is electron charged. Now the carbon over here would be donating their electrons, or you can say the electrons are pulled a little bit towards this carbon. We call this effect as electron donating effect. I hope you do understand why we are talking about this. We're talking about this because now we are at covalent bonding. In covalent bonding, before any of these effects were discussed, we have discussed the term electronegativity. And when I say the word electronegativity, the first thing that comes to your mind is the capability of an atom that can attract a shared pair of electrons towards itself, which is more like a electron withdrawing effect. Yeah, electron withdrawing effect is much more related to electronegativity if we're talking about single atoms. You do understand that this one or this one or this one or this one are more electronegative atoms. They have the electron withdrawing effect. They try to withdraw the electrons towards themselves. So if the H were not present over here and this was Cl, what's going to happen is that we can draw the arrow towards this side. This would try to drag the electron to this shared pair towards itself and select negative. So any alkyl group has an electron donating effect, the opposite to what electronegative atoms are. Yeah, opposite to electronegativity can be considered as electropositivity, which is a habit of metals. That's understandable, but we're not talking about single electrons anymore. Since we're talking about complete group of atoms, or parts of chains or branches over here. That's why we have different names than just electronegativity or electropositivity. So what I'm trying to do over here is that I am combining both of these single atoms as well as group of atoms to make sure that you understand the point I'm trying to make. I'm going to keep going with the words of the book to make sure that we understand every line over here. Now, we say that alkyl groups have a positive inductive effect. This effect will now be named as inductive effect. Inductive effect would be the effect that usually the chains have and organic chains have because of the atom or group of atoms may contain a more electronegative or a less electronegative atom. So the inductive effect would either be positive or negative. Positive inductive effect is more like electron donating effect, and negative inductive effect is going to be electron withdrawing kind of effect. So what happens is that alkyl groups push electrons away from themselves, reduce the charge density of the positive charge on the carbocation. This has the effect of spreading out the charge around the carbocation, making it energetically more stable. This means tertiary carbocation with its three electron donating alkyl groups is most energetically stable. Now, this is a little bit difficult to explain in terms of chemistry, so I'm going to rephrase it in such a way that it's more understandable for you. Because if I stick to this boring chemistry part, this might be very difficult for you to understand. So what we're going to do is that we're going to bifurcate into different types or names, more understandable. Let's consider this carbon, which is positive because of electron deficient. Let's consider that it is money deficient. All right. These can be considered as good friends. The arrow signs depict that they are going to support this carbon atom, the positive inductive effect. This supports the carbon atom by giving their own electrons to it, which you would usually do if somebody is actually deficient. Let's consider it money deficient. You're going to support him. How? You're going to give some part of your money to him to support him. Positive effect. All right. So it's a much better way of understanding. So if there are three positive effects, now this carbon would be much more stable. Imagine someone who is in need, who is deficient of money, and actually has three helpers with him. Would he be more stable? Or someone who is in need, he has one helper, but actually two people who are there to take the money from him? Who would be more stable? Who would be less stable? That's how I usually bifurcate H's and R's. Now we have fun names in Punjabi for S's and R's. I'm not gonna say that out loud in my recording, but yeah, you can come up with any fun names or any other thing to remember that this carbon is deficient, electron deficient, and R is more like a helper, and H is more like something who is already dependent on him. So he's going to take his keep. Make sense?
Sir, I have a question.
Yes, sir.
Go ahead.
Sir, when we are naming, so suppose we are naming a tertiary carbocation, so we'll use the word carbocation in the naming or no?
Naming is very much different. Now, this is a very broad category question. Carbocations are usually named as per the sections they have, which actually changes the whole thing. By section, I mean the part of homologous series they have. This can be alkyl group with another atom attached to this R or this R or this R. How would I answer that question if I don't know the atoms themselves? But the
So
old way
let's
of
say we
naming
have
had the word
so let's say
carbocation
we
to
have
them.
alkanes.
Alkyl chains
No, if we have alkanes, like instead of R.
are alkyl chains, right? Alkyl groups, simple alkyl groups. So we're gonna go for the straight longest carbon chain. That's it. That's how we name it.
Okay, so we won't add the carbocation in the name.
Old method, yes, we do add the word carbocation. New method, no, we don't. The word
Okay,
carbocation
sir.
doesn't need to be there. Okay? That's actually a part of trivial naming in which we use the word carbocation with this. And we tend to name, for example, this one is CH3, this one is CH3, this one is CH3, for example, and we call it trimethyl, sorry, bimethyl, this one dimethyl, and this as a part of the chain, and then use the word carbocation with it. We tend to do the same in this case, and we go for the straight longest carbon chain, then point out the group, and then we can say it. But the carbocation word is not necessary. However, the naming of carbocations is not a part of A levels, actually. Yeah, there are some names here and there, but you are never now not supposed to name carbocations. That's the good part. I hope that
Okay,
clarifies it.
sir, got it.
Okay.
Yes.
So, uh, but you just the only one with question, or I guess there were two voices together about question. Or am I wrong? Was Ali trying to
No,
ask a
no,
question too?
no, no. I just said it was clear.
Okay, all right. Then if that's clear, let's talk about the chemistry portion. Now, why are our atoms able to, our groups able to stabilize this one? Remember, when they try to donate an electron to this one, they actually take up the charge density for the whole molecule. Now, when the charge density is divided among the whole molecule, this R, and this R, because they're trying to donate their electrons that are on it, or what I tend to say is that the deficiency of money this one has is now divided among four people, so the deficiency on one person would not seem enough. एक बंदे के पास deficiency of let's say 10,000 and that is divided among four people, it's not 10,000 anymore, it's 2,500 per person. So it actually divides for everyone and seems less. So they become more stable because the deficiency seems less. In this case, it's least stable. Why? Because only one of them is capable of distributing the charge with it, the deficiency with it, right? That's how, in chemistry, we define how tertiary carbocation is more stable and primary carbocation is less stable. Secondary carbocation is right in between, which is less stable than tertiary but more stable than primary. The words are not written in the book, but the writer automatically assumes that you understand the point. Fair enough?
Yes, sir.
All right. Moving on. The more alkyl groups adjacent to the positively charged carbon atom, the more stable is going to be the carbocation. And this is the takeout from all of this. So of course, the one we calling tertiary is more stable because it has three alkyl groups adjacent to it. Okay. So as a result, tertiary carbocations are more likely to form in reaction mechanism than secondary. In secondary, more favored than primary. Primary are least favored. This has effects on products of some very important organic reactions. We are going to consider some organic reactions right after this topic, and you're going to see that carbocations are going to form as a result of heterolytic fission. And in those, in which product is going to more likely to form, you already know about it. So if I go back and just a minute. So if I go back, we started off with heterolytic fission, and we were talking about positive and negative charges. So if there is some halogen or some atom like this, and that goes out of an organic compound, it would definitely take the negative charge because of being more electronegative than the rest of the whole chain. If the whole chain is made up of carbon and hydrogen, the halogen would easily take the negative charge. And then we have a carbocation. Then what kind of carbocation would form if there is a possibility of a secondary carbocation, then a primary carbocation that would be more favorable. Keep this point in mind. It's just an initial explanation. We are going to use the same point in upcoming many chapters. If you understand this point, whenever I'm going to refer back to it, that secondary is more plausible, is more probable than primary, or tertiary is more probable than any of them, then you would understand the point. And I am going to refer back to this one. Okay. I'm going to refer back to this one in this chapter. I'm going to refer back to this one in the next chapter and the chapter after that. Since I'm going to do it over and over again, you'd understand this point completely. All right. So carbocations are actually species that we call electrophiles. Now we are going to divide species into two other broad categories, electrophiles and nucleophiles. The word phile itself means love, right? So electrophiles mean electron loving, nucleophile, which is nucleus loving. Nucleus actually because of the protons, the positive charge. So electrophile really means something that would love an electron, probably because carbocations are electron deficient. They would definitely love electrons because then they would become stable or complete. Nucleophiles, however, are usually the ones which would love a nucleus, which would love positive charge. Why? Because they might have negative charge dominant in them and they would like to get balanced. So electrophile would accept a pair of electrons. This results in formation of a new covalent bond. This is going to happen in next chapters. We'll see about that. Nucleophiles, when studying organic chemistry in their mechanism, these are electron-rich species. They might be negatively charged. This one is a nucleophile. All right. Why? It has a negative charge. It would love some positive charge to get balanced. Or something that has a partial negative charge. For example, HCl. This one is partially negative. This one is partially positive. This one is a nucleophile. When a nucleophile donates a pair of electrons, it leads to the formation of new covalent bond with the electron deficient atom under attack. And this is going to be another way how the reactions are going to happen. Now, this seems a lot of information, so I'm not going into further detail right here and now. We're just keeping them as starting points for many pieces of details or reactions. So what I'm going to do is that whenever any information related to this happens, I'm going to come back to it, explain you the same thing, go with the initial or starting lines from here, and that way I'm going to connect you with this point. So if you can't understand this point, or if you think there is too much of information in these two pages, yes, you're right, but we're going to refer back to this information so that it's easier for you to understand it. Okay.